morning, students. This lecture is in continuation with the previous lectures. Today we will discuss the factors influencing the solubility of drugs. There are various factors which influence the solubility of drugs. Number one is temperature. The solubility is directly proportional to the temperature. This means that if the temperature is increased, the solubility also increased. But sometimes the solubility decreases as the temperature increases. For example, in the exothermic process, the solubility decreases with the increasing temperature. But in case of endothermic process, the solubility increases with the increasing temperature. Okay. Now this is a graph which shows the effect of temperature on the solubility of the potassium nitrate. It shows that the solubility increases as the temperature increases. Now second factor is nature of solvent. The solubility of a solute in a solvent depends on the nature of the solute and the solvent. So solubility depends upon the nature of solute as well as nature of solvent. The polarity of the solute and polarity of the solvent affect the solubility. For example, students, polar solvent dissolve the polar solute and non-polar solvent dissolve the non-polar solutes. Okay. Now this is the effect of nature of solvent. Third is effect of pressure. The solubility of gases is increased by the increase in the pressure. Okay, as the pressure increases, the solubility of gases increased. There is a direct relationship between them. For example, gaseous CO2. It dissolves in the liquid for effervescent preparations under pressure. Okay, now Henry law dictates that the temperature is constant. The solubility of the gas corresponds to its partial pressure. Okay, you can see the Henry's law. This is the equation for the Henry's law. P is equal to KHC, where P is the partial pressure of the gas, KH is the Henry's law constant. Okay, and C is the concentrate of the gas in the liquid. Okay, you can see that it is directly proportional to the pressure. Okay, now next is this formula indicates that at a constant temperature, when the partial pressure decreases, when P decreases, the concentration of the gas in the liquid decreases. Okay, you can see in the equation now, P is directly proportional to C. When P decreases, then C also decreases. Conversely, when partial pressure increases, in such a situation, the concentration of the gas in the liquid will increase. Okay, as well as solubility also increases. So this is the effect of pressure on the solubility. Okay, next is the fourth factor is the pH. Okay, for non-ionizing substances, solubility can be enhanced by change of dipole moment. pH has little effect on non-ionizable substances. For example, the pH depends on the Henderson-Hasselbalch equation. This is the Henderson-Hasselbalch equation for the acidic drug. pH is equal to pKa plus log S minus S0 upon S0. Okay. And for basic drugs, the Henderson-Hasselbalch equation is pH is equal to pKa plus log S0 upon S minus S0. These are the two equations, that is Henderson-Hasselbalch equations for acidic drugs and basic drugs. In these equations, students, you already know what is pH, pKa, dissociation constant. Okay, S is the solubility of the substance, S0 is the solubility of unionized species, and S minus S0 is solubility of ionized species. Okay, pH of a substance is related to its pKa and the concentration of ionized and unionized form of the substance. You can see that solubility increase with the increasing temperature, so increasing pH. Okay, graph A, graph B. Graph A is a weak acid and graph B is for weak base. Okay, the fifth factor is particle size. As the particle size decreases, the solubility increases. Okay, due to the increase in surface area. Students, you already know that when the particle size will decrease, smaller the particle size, greater is the surface area and greater will be the solubility. However, in some cases, decrease in the particle size decrease the solubility due to the formation of agglomerate. Agglomeration is solvates, then it comes anhydrous, then it comes hydrates. This is the range of solubility for these substances. Next factor is the molecular structure. The change in molecular structure strongly affects the solubility of a compound. For example, introduction of the hydrophilic group into a hydrophobic substance, it improves the solubility. Okay, so by changing the molecular structure, we can enhance the solubility of the compound. Eighth factor is solute-solvent interactions. Solute-solvent interactions influence the affect the solubility. The relationship between solute and solvent is very important in determining the solubility. Strong solute-solvent attractions equate to greater solubility, while weak solute-solvent attractions equate to lesser solubility. Means stronger is the attraction between solute and solvent, and greater will be the solubility. Weaker the attractions between the solute and solvent, and lesser will be the solubility. So students, these are the 8 factors which influence the solubility. Okay. Next topic is solubility of gases in liquid. That what is the solubility of gases in the liquid? The solubility of the gas in the liquid depends upon the various factors such as temperature, pressure, nature of solute, solvent, nature of the gas. We have already studied these factors. Okay. Now Henry's law we have also studied. Henry's law states that the solubility of the gas in the liquid is directly proportional to the partial pressure, that is P, okay, of the gas at the constant temperature. It was formulated by the William Henry in 1803. Henry law, S is directly proportional to P, where S is the solubility of the gas, P is the partial pressure, and K is the Henry's constant. Okay. If the solubility measurement is based on the molar fraction of the gas in the solution, then Henry's law states that partial pressure of vapor phase P is proportional to the molar fraction of the gas X in the solution. Okay, means P, that is partial pressure of vapor phase, that is P is equal to KHX, where KH is the Henry's law constant and X is the molar fraction. Okay. Now students, you can see this is the graph between the partial pressure of the gas in vapor phase. Okay, partial pressure of the gas in vapor phase on y-axis, and on x-axis that is molar fraction of the gas. It means that partial pressure of the gas in the vapor phase is directly proportional to the molar fraction of the gas. Okay, the concentration of dissolved gas depends upon the partial pressure of the gas. Okay, the partial pressure is low, then concentration of gas also less. Figure A represents, it shows that low pressure equilibrium at low concentration. If the partial pressure is doubled, the number of collisions with surface will also double. Okay, collisions will increase, and eventually it will produce more dissolved gases. That is B figure. It represents the double pressure equilibrium when concentration of gas is doubled. Henry's law applied to the increase the solubility of carbon dioxide in carbonated drinks and soda water. The bottle is sealed under high pressure, but there are still limitations of the Henry's law. Okay, there is no chemical reaction between gas and the solvent. The gas should not undergo dissociation in the solvent. Okay, pressure of the gas is not too high and temperature is not too high. These are the conditions on which the Henry's law is applicable. Next law is Raoult's law. Raoult's law you have already studied in your previous classes. It states that the partial vapor pressure, that is Pi, of each component in a solution is directly proportional, directly related to the mole fraction, that is Xi of the component in the liquid, and vapor pressure of the pure component, that is Pi star. It states that Pi is equal to Xi into Pi star, where Pi is vapor pressure of the component, Xi is the molar fraction of the component, and Pi star is vapor pressure of pure component. solution of two liquids, for example A and B are two liquids, then total vapor pressure P of the solution is equal to the sum of pure vapor pressure of two components PA, PB. These are the vapor pressure of the A and B. Thus, the total pressure will be represented as P is equal to P star A into XA plus PB star into XB, where XA and XB are the molar fraction of component A and molar fraction of component B. Okay. Now, there are various limitations of the Rolle's law. Rolle's law is applicable only to the very dilute solutions. This applies to solutions containing only a non-volatile solute. This does not apply to the solutes that dissociate or associate within the particular solution. So students, these are the limitations of the Rolle's law. Now under the Rolle's law comes two definitions, that is binary solutions, ideal solutions, non-ideal solutions. First of all, we will discuss about the binary solution. It is a combination of the or mixture of two completely miscible liquids. Binary solution is a combination of two completely miscible liquids. The boiling point of binary solution based on the composition of the solution. Okay. Now ideal solution. We have studied Rolle's law. So ideal solutions are the solutions which obey the Rolle's law in all the solute composition in a solvent at all the temperatures. Means those solutions which obey the Rolle's law under the all conditions of temperature. These are called as ideal solution. For example, two liquids A and B form an ideal solution when the molar attraction between AA and BB are identical. Therefore, molecular attraction AB will be almost identical to the molecular attraction AA and BB. Means two molecules are there, na? Two liquids are there. The molecular attraction between AA and BB, these are same. If these attractions are same, then the attractions between the AB will be identical to the AA and BB. Students, you can see this phase diagram of the ideal solution. Vapor pressure is on the y-axis, molar fraction is on the x-axis. Okay. You can see this is the graph between the vapor pressure and the mole fraction. Okay. Here P is equal to PA plus PB. PA is equal to XA into PA star. PB is equal to XB into PB star. Okay. These solutions obey the Rolle's law in all the compositions of solute in the solvent and at all temperatures. Now, various characteristics of ideal solutions are, they obey the Rolle's law, that is PA is equal to XA, PB is equal to XB. No heat absorbed or evolved during the mixing, means delta H mixing is equal to 0. No expansion or contraction on mixing, means delta V mixing is equal to 0. Okay. Now, second solutions are non-ideal solutions. They are also called as real solutions. Non-ideal solutions are those solutions which do not obey the Rolle's law over entire range of composition. Okay. The ideal solutions are those solutions which obey the Rolle's law, and non-ideal solutions are those solutions which do not obey the Rolle's law. Okay. Here PA is less than XA, P not A, and delta H mixing is less than 0, and delta V mixing is less than 0. In this case, solution of this type show negative deviation from Rolle's law. Okay, they show the negative deviation. You can see in the diagram. This is a phase diagram of solution showing negative deviation from Rolle's law. Here, PA is less than XA into P not A, and delta H mixing is less than 0. Delta V mixing is less than 0. It shows a negative deviation from the Rolle's law. When the adhesive forces between the molecules of A and B are greater than the cohesive forces between AA and BB, means forces between A and B are greater than the forces between AA and BB, the vapor pressure of solution is less than expected vapor pressure from the Rolle's law. So these show the negative deviation from the Rolle's law. Okay. Now the second condition is there. When PA is greater than XA into P naught A and delta H mixing is greater 0. Delta V mixing is greater than 0. This shows the positive deviation from the Rolle's law. Okay, we have studied now earlier negative deviation from Rolle's law. Second condition, we can see the positive deviation from the Rolle's law. This is a graph, phase diagram of the solution which shows the positive deviation from the Rolle's law. Here, PA is greater than XA into P naught A. Okay, this is the positive deviation from the Rolle's law. That's all for today. Thank you.